Hi, I'm Changliu Liu, an assistant professor in the Robotic Institute at Carnegie Mellon University. Today I'm going to talk about our recent work on the verification and adaptation of deep neural networks. Deep neural networks have been widely used as nonlinear function approximators in various applications, ranging from computer vision to control. In particular, in our work, we used them to encode control policies for delicate robot assemblies, to build models for human motion prediction, and to learn control policies for efficient human-robot collaboration. These applications are all safety critical. We need to ensure that the deep neural networks correctly represent the desired functions we need and are robust to disturbances. As a function approximator, we evaluate the robustness of the neural networks by checking the following input-output relationships. That is, given all possible inputs belong to the set curly X, all the outputs from the neural network should belong to the set curly Y. One example of the input-output relationship is shown below in a human motion prediction task, where we map the image to a future trajectory of that human. Here we want to ensure that even if the image is perturbed, for example, changing the light condition, changing background, or add some random perturbation, the predicted trajectory should not change too much as long as the input perturbation is bounded. To prove robustness of those neural networks, we need to perform offline verification of a trained network in order to formally check its input-output properties before deploy it. In the following discussion, we will introduce our toolbox neurowerification.jl for sound verification. And meanwhile, if a network is found to be problematic, for example, fails the verification, we need to repair the network by adaptation, that is to update the network parameters to compensate the error. And then we'll talk about how we can do this efficiently and how to verify this adaptation online. So a verification problem consists of two parts: the function to be verified and the specification or the property that needs to be checked. Here, we consider the input-output properties, which is encoded in two sets, this curly X and curly Y. And then essentially function f, curly X, curly Y, forms a verification problem. And then we'll call verification algorithms to tell us whether the claim that f maps curly X to curly Y is hold or is validated. And the neurowerification.jl toolbox implements a variety of algorithms that can answer this question. So conventional point-wise validation methods cannot correctly answer the question if the set X is a continuous set. That is, it contains uncountably many points. One example is shown here. Suppose the neural network F maps the horizontal axis X to the vertical axis Y. We want to verify that for all X in the origin range, the output Y should lie in the blue range. So in other words, the graph of the function encoded by the neural network should be bounded by the gray region. And apparently from this figure, the function does not meet this specification. However, if we do point-wise validation by sampling the input range, for example, as shown in the figure, we sample those red dots, it is possible that we miss the peaks of the function that violates the constraint and arrive at a wrong conclusion. So neurowerification.jl implements a variety of existing sound verification methods that overcome the problem in conventional validating approach. We have a survey paper on this topic, which has just been accepted by Foundation Trends in Optimization, which is cited below if you're interested. These methods draw insights from the following three categories of analysis: reachability, optimization, and search. Reachability-based methods propagate the input set, as shown here, as a geometric object layer by layer to obtain the output reachable set, and then compares the output reachable set with the output constraint. So sometimes for computation efficiency, the actual reachable set may be over-approximated using other geometric objects during this layer-by-layer propagation. That can save some computation power, but potentially may lead to inconclusive results. And then optimization-based methods formulate a constraint optimization to falsify this input-output property. That is to find an input x belong to this curly x, but is not mapped to curly y. And the network is usually added to the optimization problem as an equality constraint here, which is highly nonlinear and non-convex, very difficult to deal with. And there are different methods that has been developed to simplify this equality constraint. For example, we may relax the graph of a ReLU activation as this triangle area, or use mixed integer encoding to directly encode the ReLU activation. Similarly, this relaxation may also introduce over-approximation and lead to inconclusive results. To minimize the over-approximation in the reachability or optimization-based methods, we may use the idea of the divide and conquer and search through different partitions. So for example, we may divide or partition the input space into smaller pieces and then run either the reachability analysis or optimization methods on these smaller pieces. If the result on any partition is inconclusive, we may then divide that partition into smaller pieces again and again until we arrive at a conclusive result or timeout. So existing approaches are able to handle piecewise linear activation functions and some nonlinear activation functions. A majority of the methods focus on feed-forward networks with ReLU activations. There are 3 criteria to evaluate a method or a solver: soundness, completeness, and termination, where termination means whether the method terminates in finite amount of time. We will say a method or an algorithm or a solver, they're equivalent, is sound if the property actually holds whenever the solver returns hold. And then we'll say a method is complete if the solver returns hold whenever the property actually holds. You may view the soundness or completeness as necessary or sufficient conditions. A solver that is sound and complete and terminates in finite amount of time will always output the correct result conclusively without any unknowns. And the point-wise testing method that we discussed earlier is always complete but not sound. The reachability and optimization-based methods that introduce over-approximations is sound but not complete. So all the methods in our survey and implemented in Toolbox are sound, as the soundness is the most important property for safety critical applications. And among these sound methods, there's a trade-off between the completeness and the computation efficiency. That is, people sometimes sacrifice the completeness to achieve highly efficient computation. And this is an open problem to solve in terms of how to attain both completeness and the computation efficiency at the same time. So each algorithm in our Toolbox will return one of the following 3 types of violation results if a property is not hold. So the first is a counterexample result, where a counterexample belongs to the input constraint but is mapped to a point outside the output constraint. And the second is the adversarial result, that is the maximum deviation allowed in the input space to still meet the output constraint. If there's a violation, then this maximum deviation is smaller than the radius of the input set. And the last result is the output reachable set. If there's a violation, the output reachable set will exceed the output constraint. So one advantage of having different algorithms that are previously implemented in different platforms to be re-implemented here in our Toolbox with the same environment and same standards is that we can better compare their actual algorithmic advantages without worrying about potential biases introduced by different implementations. And we did extensive comparison and analysis on these methods implemented in our Toolbox and obtained many interesting findings that are summarized in the survey paper. One example is shown here. We compared the node-wise bounds computed using different reachability and optimization methods, and it is very surprising to find that AI squared Z, reachability methods use xenotope as geometric templates actually provides the same bounds as conv dual, which is a dual optimization method that uses parallel relaxation of value activations. And in terms of computation time, conv dual is faster on wider networks, and AI squared Z is faster on narrower networks. And of course, further study is needed to have better understanding of the underlying mathematical connections. But these findings motivate our current work, that is to compose different algorithms or methods together in order to leverage their unique advantages in solving real-world problems. This composition can naturally happen within our toolbox if we add an additional layer to existing solvers. So for example, if a user wants to compute node-wise bounds, then we may just add a level of check to check the property of the network. If the network is wide, then we select conv dual. If the network is narrow, then we select AI squared. Okay, so that is for the verification side. If the verification process returns violation, for example, we find a counterexample in the network, then we may need to repair the network by adapting the network parameters with respect to the counterexample. However, it remains unknown in terms of how to efficiently perform this adaptation and verification process efficiently and effectively in order to finally converge to a satisfiable network. But here, actually, we're considering or more interested in a slightly different case where we want the adaptation in the sense that we want to adapt the network parameters to meet other performance requirements, while we still want the network to satisfy a fixed safety specification. So for example, this happens in the human motion prediction case. The human behaviors are highly heterogeneous and time varying. And so then it is ideal to adapt the prediction model encoded as a neural network, to adapt that online in order to minimize the real-time prediction error. And with that, the challenge is that how can we ensure that the adapted network still satisfies the safety specification? And this problem can be rephrased as how to maximize the real-time performance of a neural network while satisfying safety constraints. So to perform this adaptation safely, we have different approaches. One way is to perform this runtime verification together with the adaptation, and only check the adapted network when it meets, or only execute the adapted network when it meets the specification. Or a second way is to directly constrain the network parameters with respect to specification in the adaptation process. Here, we're focused on the first approach. And the challenge for the first approach is that existing verification algorithms are computationally expensive to run in real time. But there's a good thing happen for the adaptation. That is, during the online adaptation, the network parameters actually do not change significantly. The new verification problem is actually similar to old verification problem that has been verified previously. And in this way, we may just reuse some of the previous verification results to perform efficient sound runtime verification. And this idea of reusing old results essentially leverages the memory efficiency for computation efficiency. And there are many ways to use old verification results to warm start new verifications. For example, we can perform incremental analysis in terms of incremental search, so that we can remember previous search tree and reuse those unaffected branches, only adapt those branches that will be that is changed with respect to new network parameters. Or we may verify a relaxed problem using interval networks that covers a range of possible network parameters and only re-verify the problem if the actual parameter lies outside the range. These two approaches can be applied on top of any existing method. And we did a simple test on top of Neurify in our toolbox, and the result is shown on the table here. So we can see these two approaches actually successfully reduces the computation time from 6 seconds, where we always do the verification from scratch to 0.3 seconds, which is 20 times faster and ideal for real-time application. Nonetheless, there are still a lot of work to do in order to underline the basic mathematical principles underlying these methods and to apply these methods on real-world problems. Okay, in summary, this talk introduces basic principles for verifying input-output properties of deep neural networks. And the neural verification toolbox is also introduced. Then we talked about ways to apply existing methods in problems that require runtime verification of adaptable networks. I would like to thank the sponsors, Cars and Ford, who supported the work presented here. And also we are organizing the second BN Comp. You may find more details of this competition in the following link. With that, I would like to thank you for your attention and feel free to reach out to me if you have any question.